Let's talk Displayport and the just awful task of bringing to life the Displayport specification and what it means for you, because you probably got a new display. Maybe does it have some problems? Are you having problems with your Displayport display and you don't even realize? Black screens and cutouts, things like that. It could be your cabling. And also, I bought a $15,000 cable tester, which is crazy. Let's talk about why. This is a new model KVM that I've been working on. It's 120 watt USB-C power delivery. So you've got two USB-C inputs, one regular DisplayPort output, and then there's a USB hub in here. There's a physical switch picking if you want to do USB 2 or USB 3, because there's not actually enough bandwidth to do 4K 60 444 uncompressed with 5 gigabit USB 3 on this type of connection. So it's a lot of work. Okay, let's break down DisplayPort, the cable specification. Let's go to the whiteboard. Originally, DisplayPort was created to be a simplified interface for a direct to LCD panel connection. Manufacturers really didn't want to have a controller inside an LCD display, and it was called Embedded DisplayPort. And Embedded DisplayPort is still there. In fact, the iPad miniature DisplayPort interface thing that I built a couple of years ago that's popped up on the channel from time to time, that's Embedded DisplayPort. That little tiny LCD panel uses EDP. The 27-inch iMac, I think it was like the 2008 or 2009 iMac, that 27-inch panel also embedded DisplayPort. Some of the monitors that I've imported from Korea, been a real big fan of those, like the glossy finish, the 2560 by 1440, embedded DisplayPort. Now, sometimes they do have a controller that'll take something from the input signal and do something with it, and then pass that embedded DisplayPort signal on to the display, but it was really meant to be a low-cost, let's just get around having to have a controller inside the monitor at all, and let the actual computer control it. But to my knowledge, Apple are the only people that have ever actually implemented it that way, meaning that the color correction happens on the GPU, the brightness control even happens on the GPU. There's not really anything in the display to be able to do any of that. It's all controlled at the protocol level, and that's exactly how it works on the iMac. That's exactly how it works on the iPad, but I'm not really aware of a PC equivalent monitor that was done that way, because nobody wants to control brightness from, a Windows app. I'm not even sure that Windows ever actually built that. The actual DisplayPort interface, if you look at it, is pretty interesting. So I'm talking about desktop DisplayPort here as well. So there are 4 lanes. Now, things get a little sketchy if you go really far back. I'm really talking about DisplayPort 1.2 and forward to 2.0. 1.0 and 1.1a bent the rules a little bit between specification and implementation. It was a little bit of a headache on the first version of the KVM, but there are 4 channels for display data. There's another channel for aux, and there's a hot plug detection signal, which they've actually stuffed a couple of, this is toggled on and off rapidly in some scenarios to actually communicate data. This is generally a one-way interface. Aux is generally a 2-way interface. The original 1.2 specification said that this could run at 1 megabit or up to 720 megabit. The Visa committee actually thought people would use USB over this. I think Dell implemented that in some of their displays, but there you go. In DisplayPort 1.2, a single one of these channels is enough bandwidth to do 1680 by 1050 at 60 hertz. So a lot of DisplayPort cables that we've tested might have the first channel or 2 using the best pairs, and the second channel or 2 using the worst pairs. So our total phase cable tester, we've got some examples of that. If you check out the eye diagram here, this shows what we're talking about. You can clearly see a difference between the first pairs and the second pairs. This means that the cable manufacturer has actually bent the wires that are in use on the cable. They've put the better cables for the first 2 pairs, meaning that it'll work with lower resolution and refresh rate devices, and the other 2 channels are there because they have to be there because of the specification, and they actually do pass specification for 1.2 according to our total phase cable tester, but visually in the eye diagram you can see. Now, if I digress for a second, we talk a little bit about eye diagrams. You think of a digital signal you got highs and lows. And in an ideal world, things goes from high to low really rapidly. But the wire itself can act a little bit like a capacitor, which means that it'll store charge and it'll hang on to charge a little bit after you stop sending charge. And I'm oversimplifying a lot here. I don't want to turn this into an EE video, but even though the signal that you're putting into the wire is a nice clean square wave, the other end of the wire, the things can kind of be rounded off a little bit. And so this is what your eye diagram is. This is showing 1 0 1 0 1 0, but if you had 0 1, something like that, it would show you what's going on. So the eye diagram is lots and lots and lots of signals overlaid with one another, showing you, hey, are we actually in the keep out zone? So like you've got from here to here for your level change from a 1 to a 0 or a 0 to 1. This depends on the timing actually on the wire. And then you have your spot in the middle, and then everything else goes that way. So in order for highest resolution and highest refresh rate devices to work, like if you wanted to run the full 4K 60 hertz on your display, you actually effectively have 1, 2, 3, 4 1920 by 1080 60 hertz quadrants. Now, it's not sent on the wire as 4 1920 by 1080 60 hertz quadrants, but there is that amount of bandwidth when we're talking about DisplayPort 1.2 using all 4 channels. So all 4 of these wires have to be equivalent, otherwise you're going to run into problems. And if we have a 1 or a 0 going through the middle of our eye diagram, that means that things have actually failed. Now, this cable tester tests the cable for a very short period of time. Suppose your microwave oven kicks on and it's sitting right next to your computer. Your display blacks out. What happened? Well, there was momentary electromagnetic interference that caused a loss of synchronization on this signal, and the display blacks out. Because it's a digital signal, it either works or it doesn't. So if your display intermittently blacks out, the cable can still pass a test, but you can sort of learn to eyeball the diagrams and say, okay, this one definitely looks better than the other one. This cable is more dodgy, or this cable is less dodgy. There's also the idea of ferrite filters. I don't want to get too ahead of myself here, but a ferrite filter is basically a magnetic clamp. Sometimes it's called a ferrite bead. I was taught by an old school person, so they always refer to it as a bead, even though it's more of a cylinder these days. It was a bead in the old days. And what this does is it attenuates high frequency signals so that there is more resistance on the wire for high frequency signals. And that might sound like, well, wait a minute, this is a high frequency signal. You don't actually want that. There's a whole other component of this that happens at the PHY level that's a handshake. And so you can use a ferrite clamp, which will sort of change the characteristic of what this looks like on the wire, but it will actually cause the graphics card or whatever you've got plugged into it to adjust the pre-emphasis and the gain and some other physical characteristics that you don't have any access to in software in order to provide a better signal. And so just as anecdotal evidence, generally like Vega 56 and Vega 64 GPUs have a much weaker signal output. Their training for cable training is generally a lot worse than other video cards. It's worse than Polaris. It's worse than the Navi cards that followed. I think that they've corrected those issues, but the DisplayPort out is pretty sketchy on those graphics cards, and so they fix it a little bit in software. And actually, the AMD driver software exposes some options, including pre-emphasis, that you can set in software in case you're having actual display problems. And our total phase cable tester lets us test the cables, but it doesn't let us sort of see on the wire what's happening between a GPU and a display. That's just stuff that I've learned from working on these things over the years. Anyway, so 4 signaling channels, this is where most of the communication takes place. Now, this can also be super buggy, and a handshake can also be super buggy. So with DisplayPort 1.2, we're talking about a certain signaling rate. With DisplayPort 1.3, it's an increased signaling rate. DisplayPort 1.4 is about 8 point something gigabits per channel. We're going to talk about USB-C and Thunderbolt, don't worry, but the total phase cable tester can also test 10 gigabits per channel. 10 gigabits per channel is an overestimate. But there's something really interesting that happens. You see, on the wire, at the connections, and depending on how the wire is bent and other things, you can have reflections and interference. So it is possible to have a DisplayPort cable that will test fine at 8 gigabit DisplayPort 1.4, but will not test fine at DisplayPort 1.2 or a lower signaling rate because of reflections or other radio interference. Usually you can solve that with a ferrite clamp, a ferrite bead, because it's just reflections. It's a reflected signal that's causing that, not actual interference, not actual crappiness of the wire. It's just the wire's picking up its own sort of self-noise, and so it'll work at a lower rate but not a higher rate, or it's a little sketchier at a lower rate but not a higher rate. One way you as the user might notice that is if you've got 144 hertz display and it works at 144 hertz, but it doesn't work at 120 hertz, but it also works at 90 hertz. Depending on how it's using which channels on the wire, you can have some problems at certain frequencies but not others. Now there's also another pin that we didn't talk about. It's the power pin. There are certain DisplayPort cables out there that are advertised as 20-pin DisplayPort cables. You should flush those into a volcano. They're not supposed to exist. You're not supposed to have a DisplayPort cable that has the 20th pin. You've got adapters like these. This is a fancy Club 3D DisplayPort to HDMI 2.1 adapter. This is a less fancy DisplayPort to HDMI adapter. There are electronics in these. The 20th pin is 3.3 volts at a half an amp according to specifications. Some video cards can actually provide more power than that, but that provides the power for the electronics to actually do the conversion. Notice the big bulbous one. It's like, is 1.5 watts enough to power this? And the answer is no. It actually has a USB-C input because 4K 120 hertz from DisplayPort is tricky to do, and even this one doesn't work correctly, and I'm waiting for the new chipset that's actually pretty good in order to deal with 4K 120 hertz. Oh, and variable refresh rate, going from variable refresh rate on DisplayPort to HDMI, you can forget that. There isn't even anybody working on silicon to do that. You might be able to do it with an FPGA, but who wants a $700 video adapter? Certainly no one would be working on that because that's just lunacy. But I digress. So other sorts of fun things that we've run into in cable testing. This DisplayPort cable doesn't work if it's bent a certain way. Yeah, it'll pass some ways, but you sort of bend it around another way, doesn't work. I've also got the Asus 43-inch gaming monitor, 120 hertz, 4K 120 hertz out of the box. It doesn't work. Its own cable is awful. Its own cable is terrible. It doesn't work. It fails the cable test. It's that bad. But hey, a new cable fixed me right up. No more black screens and cutouts and weirdness. And it's worth noting that because of the handshake protocol, because the card can mess with its own gain and pre-emphasis, and you don't have any insider visibility into that because it's something that's happening at the physical level, you can have a video card and a cable and a monitor that work together, and then you switch your video card, and then that video card doesn't work with that cable and the monitor, but it's actually not the video card's fault, it's the cable's fault. Just so happened that the other video card that you had before could, slightly overdrive it. Or what usually happens is in that physical handshake protocol, it's usually not perfect, there's a few bugs. And so where the physical handshake should increase the pre-emphasis, it doesn't. That's really the bug with the Vega 56 and 64, is they're a little more forgiving. Like they'll handshake, and there was some noise in the handshake. It's like they didn't get quite a firm grip. It was like one of those like not exactly, there's something wrong handshakes, and they don't do it over. And so because of that, the rest of the signal, the stuff that's going on the wire, is impaired. Now there's another variable that enters the equation here, and that is display stream compression. So we've got these 4 channels that are 8 point something gigabit, but there are monitors out there that are 4K 144 hertz. How does that work? Because if you do the math, 4K 120 hertz fits on this, but not 144 hertz. Display stream compression. This is a kind of lossless compression that's happening in software. See, remember, this is a packet-based medium. This is not a lot different than PCI Express. Basically everything is doomed to reinvent PCI Express. Probably DisplayPort 2.0 or 2.1 will be some form of PCI Express because that's a packet-driven protocol, and DisplayPort is a packet-driven protocol. It's packets of data. And so this ends up being a compressed protocol if you have a chip on the other end that can decode it. So GPUs will do the compression on their side because that's not a lot of overhead for a GPU. They're really good at that kind of thing. It's almost unnoticeable. Built into the hardware, and it'll send it on down the stream to the display. The display will decompress it, and it is lossless. So 4K 120 hertz is really no problem. It adds a tiny little bit of latency overhead, But when we're talking about a 60 hertz refresh rate, that's 1/60th of a second, or 16 milliseconds. 120 hertz, it's easy to do the math, it's about 8 milliseconds. So if your compression and decompression takes less than a millisecond to do, you're not really adding any latency to the overall display pipeline. I just thought it was interesting that mostly Displayport is an uncompressed protocol. So that's a really physical, crazy amount of bandwidth on the wire. And when we're doing testing with the cable tester, it's dumping an insane amount of bandwidth onto the wire. But it's also doing a bunch of different patterns of ones and zeros, because it's just, 1 0 1 0 1 0 is sort of a best case scenario for signals on the wire. And so the test patterns that are sent over the wire can actually expose issues if it's, a gazillion ones in a row, or a gazillion zeros in a row. You can run into that not with display stream compression, but with display stream compression. So with the compression, you might end up with a long string of ones or zeros, and then that exposes a problem with your cabling or your connector or your driver or something like that. And every now and then, like, the NVIDIA drivers will regress, and all of a sudden there'll be an influx of people showing up at the NVIDIA forums complaining that display stream compression is not working. In the specific case of the Samsung G9 Neo that I reviewed, it's sketchy. The Displayport implementation with display stream compression, 240 hertz, real sketchy. And they've been able to tweak that and deal with that in firmware updates, so that's good. But sometimes you can have, NVIDIA do something in the driver to try to deal with the shenanigans of that monitor, and then something changes in the monitor firmware, and so now we've got kind of a disagreement in how the handshake occurs. And a gamer, an individual user, is just, I don't understand, it doesn't work, let's return the monitor and get an exchange or something. But really, it's actually a lot more complicated than that. I've also seen Displayport cables where the display channels are fine, but because the aux connection is so bad that the display can't handshake properly, because a lot of the handshaking, that's not the physical channels here, but like the capabilities of the monitor and the refresh rate, things like that, whatever's going on the aux channel is creating a problem. So I love that the cable tester not only tests your actual communication channels, but it also tests aux, it also tests hot plug, and it also tests the power pin, and it will fail a cable if the power pin is actually connected. I've seen everything. At this point, I've seen everything as far as Displayport cables go. It is bananas. And we're only talking about Displayport. We're not even talking about USB-C to Displayport. Now you might be thinking, wait, isn't it just the same protocol but a different physical connector? No, there are different electrical characteristics as well. At least potentially there can be. It depends on a couple of factors, but mostly there are active USB-C to Displayport cables, meaning that they have electronics inside them. There's also this idea of bidirectional USB-C cables, because sometimes you can go from a USB-C port on a laptop to a Displayport connection on a monitor, but you could also go from a Displayport connection on a device to a USB-C connection on a monitor. We have, Apple to thank for that. And USB-C is not the same as Thunderbolt. I mean, architecturally, they're kind of similar. Displayport has 4 channels. Thunderbolt has 4 channels. Thunderbolt is 10 gigabits per channel, and Displayport is 8.4 gigabits per channel. 4 channels, and then 32 versus 40. You get a little bit more bandwidth with Thunderbolt, but it also doesn't take into account the overhead of the actual Thunderbolt protocol. So, yeah, fun times. I don't want to get too off track, but we've been had. Consumers, I mean. So, remember when I said this was packet switched? So this is 4 channels on a bus. It's data packets. Do the bus care what kind of data packets they are? Generally, no. And that was kind of the promise with Displayport beyond 1.2, is Visa and Intel, for example, would get together with Thunderbolt. Now, Thunderbolt has the promise and has the capability to use these 4 bus channels, and even the aux channel for control, and provide a fully packet-switched network for both data, for the display, as well as USB. So USB 3, 5 gigabit, not USB 3.2 Gen 1, 5 gigabit, and 32 gigabits of traffic here on this channel. Let's say the Thunderbolt variant, round up to 10 gigabits per channel. Again, it's not really an apples to apples comparison, but 32 plus 5 is less than 40 gigabit. We ought to be able to do it. Thunderbolt can do it, but pure USB-C, pure Displayport cannot. So think about an adapter that is into your laptop for USB-C that would give you USB output or USB socket and DisplayPort. That would be amazing. That was one of the first problems that we ran into working on the KVM. It's like, I would love to have a single USB-C connection from a laptop that breaks out into DisplayPort as well as USB. But it turns out to do that without Thunderbolt, you've got to either agree not to use one of your channels, which is going to limit your resolution and refresh rate, or you've got to use your aux channel, which is going to be limited to about 720 megabit. See, the VESA standards people never really beefed up the aux specification to be able to allow 5 gigabits. So we don't really have cables that'll allow 5 gigabits, and it is a disaster area, as we've seen, when you have a cable that's physically compatible but not actually electrically compatible with the new signaling rates. Thunderbolt was a promise to fix all of this, because with a Thunderbolt interface, because it's packet switched, you can basically have an adapter on this side that's muxing your two sources of packets onto the bus wherever they'll fit. You can basically take any lane on the highway as opposed to a fixed designated lane and losing some overhead, and get USB and DisplayPort out the other side. This is a problem with the power delivery version of the Level 1 Text KVM, because there's a physical switch on the back that lets you pick. Do you want USB 3 speeds and 444 chroma at 4K 60, or do you want USB 3 speeds, 5 gigabit, and 420 at 4K 60 hertz? Because that's all you can do, at least without display stream compression, without something on the Thunderbolt side. Now, Texas Instruments has a really awesome application note that shows going from USB-C to DisplayPort, but it leaves out the USB part of it. It just gives you DisplayPort. So if you're doing an adapter to go from USB-C to DisplayPort, then you're all set. But notice this is also unidirectional. If you have a USB-C display and you want to go from DisplayPort to USB-C, that doesn't automatically work with your cable. It's not just a matter of connecting up these 4 lanes and aux. So in the Texas Instruments application note, which is a pretty good illustration, you see that you've actually got to have some switching circuitry and some control circuitry to deal with hot plug detect, which is usually the thing that doesn't work through the Level 1 KVM because the cable assumes that it'll never be physically unplugged. Also, Apple devices are really bad about that. They implement their own hot plug detect that uses some ground pins that it shouldn't, and so you really pretty much have to use a bidirectional USB-C cable, not just with the KVM, but pretty much all Apple devices, because Apple makes a lot of incorrect assumptions about how they do their implementation. But the USB-C connection, the Texas Instruments application note, it's like, here's the IC chipset example that we give you for building a bidirectional USB-C to DisplayPort adapter. It actually will mess with the voltage level and the pre-emphasis and some of the noise and gain, but we don't need to get into the EE end of this, although it is pretty interesting that it doesn't just electrically work, because there are passive cables out there that will just passively connect these and aux and hope it works. Generally, that actually will work when we're talking about lower resolution and refresh devices. It doesn't matter that the connection is actually pretty crappy. You don't need any ICs to redrive it. But if your display is a little bit intolerant of signals, or other things are intolerant, or you're trying to switch through a KVM, it's not going to work. You're going to need an active adapter to clean that up. Otherwise, your eye diagram looks like that. And if you look at the eye diagram actually in the Texas Instruments application note, the reason it looks the way that it does is because it has all sorts of different frequency signals overlaid on top of one another. And as you can see, it really doesn't have a lot of margin on it the way that the cables do. And this is a pretty good chipset for doing the adaptation here, and you see how little margin we have in the eye diagram for those kind of implementations. And so that's why I say that, we've been robbed as consumers, because the VESA people expected somebody to make something like what Intel has with their Thunderbolt thing, which is just one mux, to basically abstract away this, so everything, all of the data travels over one packet switched network. That's much, much more efficient than the protocol that we have now, or even saying that, okay, this 4th lane is for USB, the other 3 lanes are for display. We don't, you lose a lot when you do that. You lose a lot to the protocol overhead. It's no problem to keep the signaling rate at 40 gigabit and have enough room to do 4K 120 hertz plus 5 gigabit USB, But licensing, intellectual property, patents, I don't know. Just as a consumer, something feels wrong. But that's USB-C in DisplayPort, which is, a thing. So there you go. DisplayPort. 4 channels for communication. An aux channel that initially they thought was going to be used for USB, but mostly is misused by literally everybody. You have a control channel, and then you also have a hot plug detect, which is usually just a bit or two, but hey, that can also be used to signal for a thing if you toggle it on and off really quickly. So, and Apple actually uses that one differently, which is why sometimes Apple will detect a display, but the display won't display anything. It's because the display is thinking that the device told it, hey, you said there's nothing to display. And Apple is saying, well, the hot plug detect didn't fire, the display is still here. Even though you got a big black nothing on the display, the Apple device thinks the display is working. They actually do the handshake protocol in a slightly different order than everybody else. And, because they're Apple, we're right. Everyone else is wrong. We're a $3 trillion company. But, of course, it just makes everybody's life a nightmare because that level of pedantry is what you get. But enough about Apple. I digress. I'm Wendell, this is Level 1. This has been a quick look at Displayport cable and our total phase $15,000 cable tester in the quest to build the ever better KVM switch. Woo! Those are for sale at store.level1text.com. I'm getting them in just as soon as the supply chain allows. If it weren't for the global situation, things would be a lot better. But it's not actually, you'd think we sell a ton of them, but it's really not a huge volume. It's just a niche product, and I only accept the very best of the best chips. The USB interface chips are basically hand selected. Like you pick them and you sniff them. No, this is not a good year. This is not a good vintage. We need a better USB chip. So, because if you don't, you run into problems. Anyway, I'm Wendell. This is Level 1. I'm signing out. You can find me in the Level 1 forums. If there's anything you want to test or see or do whatever. I'm also doing the front panel testing with this cable tester. I've modded it a little bit. So it's like we can do USB cable testing. But can we do USB front panel testing of cases? Because you'd be surprised. Not all cases actually have a reasonable USB-C or USB 5 gigabit front panel interface. Some of them can do 5 gig, but not 10 gig, which is, that's also an option in Type A. But most of the time for the 10 gig, they go for the USB-C connection or 2x2 20 gig, which again, not all front panel cases can actually do 10 gig on both sides of the USB-C connection. It's really interesting stuff. Anyway, I'm out of here.